Okay, so what I'd like to talk about a little bit is solving problems. So this being Phys 121, we're going to talk a little bit about solving physics problems. So now I'm sure you've all seen, these laundry lists of, strategies to solving physics problems, techniques. Draw a diagram, try to visualize the problem. Figure out what's known and what's unknown. Think about what sort of principles are involved. Is this a conservation of momentum problem? Is this an F equals ma, force type problem? Think about the principles involved. Make some estimates, make some predictions. Write down some formulas. Generate some kind of an answer. Look at that answer, see if it makes sense. Plug in some numbers. Do the answers that come out of plugging in those numbers, do they make sense? Do you get reasonable answers, et cetera, et cetera? But rather than sort of giving you that laundry list, I just like to sort of illustrate how it is a physicist would solve a problem. So we'll just pick sort of a typical problem in Physics 121, and I'll just sort of model how it is a physicist would think about that. Because at the end of the day, your physics degree is not there to give you knowledge, right? I mean, that's largely what we have the internet for. Your physics degree is there to change the way you think, okay, and to learn to think like a physicist. So I'll just solve a problem like a physicist, and I'll talk along the way, and you'll sort of see some of the solution techniques being sort of applied. And so, a solution to a physics problem shouldn't be, one sort of kinematical formula where you plugged in some numbers and got an answer. That might even be the right answer to the problem, but it's not a solution to a physics problem. A solution to a physics problem is one that illustrates, articulates clearly in words, diagrams, equations, that sort of thing, a whole set of ideas of how you thought about the problem, how you thought your way through the problem. Because at the end of the day, one of the most important skills you need to hone is the ability to communicate to other scientists, communicate your ideas to other physicists when you write research papers, that kind of stuff. So this is really a communication skill as well as exercising powerful problem-solving skills that'll help you think about the problems correctly and get reasonable answers. Okay, so we'll just sort of start with typical sort of an example. So here we have a platform. Okay, and this platform is a certain height h above some water. Okay, and there's a diving board over here. And the idea is we're going to have a diver start over here, walking at a certain rate here, get to this point, and crouch down a bit and jump. And so they're going to jump up like this, and then they're going to land on the end of the diving board. The diving board will flex down like this, and then it will flex back up, and they will launch off on a parabolic trajectory and land somewhere in the water. And what we're trying to do is figure out, at the end of the day, what is their final velocity when they hit the water? X and Y components, speed and angle at which they hit the water and so on. Okay, so the first thing you might want to do is say, okay, here's the person walking. Here's the diver. The diver is going to be walking in this direction. And so the first thing you want to do is you want to estimate, well, how fast is this diver walking? So let's indicate some directions. So we'll take horizontal to the right to be the x direction, vertical up to be the y direction. And so the diver is initially moving horizontally in the x direction with some x component of velocity, vx. And then so what's a good estimate, a reasonable guess for a reasonable value for that initial horizontal component of velocity? Well, how fast do people walk? You can look it up on Google and say, oh yeah, the average speed that people walk at is this. That's not how physicists think. Physicists just use their common sense. They just say, well, look, a step is approximately a meter. It might be 3/4 of a meter. It might be a little more than a meter if they're taking big steps, but it's roughly a meter. So each step is about a meter. How often do they take those steps? Well, it's dunk, 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 maybe about once a second, roughly. So the speed that our diver is initially moving at we'll take it to be approximately, we'll estimate it to be approximately, so an equal sign with squiggly lines means approximately. So it's approximately 1 meter per second. Okay, that's a reasonable value. And then the diver is going to come to this point, and the diver is going to crouch down a little bit and jump up. Okay, and what we're going to assume, this is not necessarily true in every case, but for simplicity, we're going to assume that that through the action of their bending down and pushing up on themselves and so on, at the end of the day, we're going to assume that the ground is exerting strictly a vertical component of force. And so that vertical component of force can change their vertical component of velocity, but not their horizontal component. So they're moving at 1 meter per second, and then they jump up. They still have a horizontal component of velocity 1 meter per second. And so what they're going to do is they're going to launch upwards in a parabolic trajectory like this, and then they're going to land down on the end of the diving board like that. And this diving board is going to be going down like this and then back up, and then they're going to launch off on some kind of trajectory like this. Okay? And we're going to assume, again, for simplicity, this is a super important skill to learn. Don't overcomplicate things. Try to look for the simplest sort of situation and understand the simplest situations first and well, before you add unnecessary complications. So again, we'll assume that the force at the end of the diving, through the action of the diving board going down, the person crouching down and pushing back up, all of those actions at the end of the day, we will assume for simplicity result in a force only in the vertical direction. Okay? So then you look and you say, well, let's see, the only forces acting on that diver in getting from here to here and finally launching are vertical forces. And remember that a force acting over time transfers momentum to a system. Okay, there are only vertical forces acting, so only the vertical components of momentum can be changing. There are no horizontal components of forces, so no change in the horizontal component of the momentum. So no change in the horizontal velocity of the diver. So the diver's horizontal velocity here is 1 meter per second. After this jump, it's still 1 meter per second as they're flying through the air. And then after this jump, still a 1 meter per second. Okay, so at this point, okay, by simplicity, just vertical forces, we will say, ah, yes, the initial horizontal component of their velocity as they launch on this trajectory is Vx initial, 1 meter per second, the speed that they were walking at. So it kind of looks like this, dung, 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 leap up, like that. And the horizontal component remains the same throughout. Okay, and so here we're basically saying, well, there's no force in the horizontal direction, so there's no change in the momentum in that direction. So we're using momentum conservation here as the principle. So we can just jot that down. So momentum conservation, that's the principle that was involved here that allowed us to end up with this velocity. So we'd applied it over here, and we applied it over here to end up with this initial component of horizontal velocity before they leap on their bigger parabolic trajectory. Okay, great. That's one important principle that we used. Okay, so now we have the horizontal component of this initial velocity at this point. Now we need the vertical component of the velocity. Okay, and so just by sketching here, so I know that the initial velocity, its horizontal component has to be this big, and so it has to be that long in this diagram. Okay, and the vertical component is this long. Okay, and so we'll call this Vy initial, and we'll call this V initial as a vector, as an x and a y component, Vx initial and Vy initial. Okay, so now what we need to do is estimate Vy initial. We know Vx initial, what's Vy initial? Well, so one way to get that, and perhaps one of the easiest ways to get that, is to think just a little bit about kinetic energy here. So the kinetic energy that the diver has just as they leave the board here, that kinetic energy at that initial point is going to be 1/2 m Vx initial squared plus 1/2 m Vy initial squared. Okay, so we know this first term, 1/2 m Vx initial squared. We know that term. This component of the kinetic energy, okay, it's associated with their vertical motion here. Where does that come from? How could we estimate what that is? Well, here's where it gets interesting. This is sort of like the fun of physics problems. Okay, so let's suppose that, they jump up here, and let's try to estimate what this energy component is here. So the first thing, it involves two jumps. There's a jump here, and there's a jump here. The diving board goes down, and as the diving board is springing up, they're actually uncoiling themselves and jumping again. Okay, so let's estimate how high a person can jump here. Okay, so again, you can look on Google, how high do people jump, or you can just jump. Okay, and then look and say, oh, that was about 1/2 meter. Great. Okay, so the distance d, we'll call this d, is approximately 1/2 meter. That's how high they can jump up. Okay, so when they're at this height, a half a meter above the diving board, they have a gravitational potential energy of, mg times d. So they got some gravitational potential energy up here. When ignoring the vertical component of velocity, when they fall down through that same distance d, they will have a component of kinetic energy associated with their vertical component of velocity equal to just m plus mgd. Okay, so when they hit the end of the diving board here after coming down, they have a component, a piece of their kinetic energy due to their vertical motion, which is just 1/2 m, it was just mg times d. And now here's where it gets really interesting. Okay, so now you say, if the diver didn't do anything, if the diver, jumped up and landed on the end of the diving board and stayed perfectly vertical like this, the diving board would go down like this, and then their kinetic energy would go to 0, and then it would spring back up, and the kinetic energy they had associated with their upward motion would be exactly the same as what it was initially before they started their downward motion. It's like a spring. Okay, so I got a spring here, and I throw a mass at it at 2 meters per second, hits the end of the spring, it slows down, comes to rest momentarily, comes back out, and it comes back out at exactly 2 meters per second, right? So this guy's going up initially, with exactly the same speed they had initially going down, okay, which you can figure out from that energy. But now we do something interesting. We say that that's not really what happens. What the diver does is this. Okay, the diving board goes down like this, and when the diving board is going down, during this period when it's going down to up here and becoming straight again, the diver starts in a crouched down position at that point. And then while the end of the diving board raises up like a spring uncompressing, they at the same time are pushing. Okay, and so they are converting chemical energy in their body into additional kinetic energy. And so they push, when they're walking here, they push up. They kind of crouch down and push up like this to jump up. And the amount of energy that they can, chemical energy they can convert, in this case into gravitational potential energy, is mgd. Okay, well then it's roughly the same amount of chemical energy they can convert into kinetic energy when they're uncoiling their body during this portion of their motion. And so we just add another mgd. And it's this extra mgd which results in the diver, reaching a higher height here than here, right? That's kind of cool. Okay, so anyways, so that's the initial kinetic energy. Okay, we figured that out. Just sort of common sense thinking. Okay, this is exactly thinking like a physicist. You just kind of work your way through it and then puzzle it out, draw pictures, think about principles, etc. Great, we got the initial kinetic energy. Once you have the initial kinetic energy, well, you know that kinetic energy is just 1/2 m times the square of the speed. So once you know the initial kinetic energy, that immediately gives you the initial speed. And once you know the speed, you have the x component of velocity, you can then determine the y component of velocity using a bit of trig. So you get vy initial, okay? And then once you know the x component and the y component of that initial velocity vector, well, then you can determine the initial launch angle, theta initial. Okay, so then you get theta initial. Okay, so now you know everything about the initial velocity that the diver had before they embarked on that parabolic trajectory. You know the x and y components, you know the magnitude of the velocity and its direction. Okay, so now we're going to go further, because at the end of the day we're trying to figure out, what is the velocity, what they hit the water with, direction and magnitude and all that. Okay, so then you say, well, I can partly get that way, get to the end there. I can just take a horizontal line here at the same level, same gravitational potential level, and what I know is that energy is conserved. And so there's some gravitational potential energy here and some kinetic energy. At the end, you have to have the same gravitational potential energy and kinetic energy. So the kinetic energy here, because it's at the same level, the kinetic energy here has to be the same as the kinetic energy here. And so the speed is the same. And by symmetry, you know that it looks exactly like this. Just take that vector. And I should also say, because there's no horizontal forces acting, the horizontal momentum is constant, remains constant. And so the horizontal component of the velocity at this point is the same as it was here and here and here and here. Okay, and and you know that the kinetic energy is the same, so this speed is the same. And so this vertical component of velocity at this point, Vy at this point, is negative, it's pointing down, and it's exactly opposite to Vy initial here. So negative Vy initial. If it was 3 meters per second up here, it's 3 meters per second down here. Okay? And another way to think about this is, obviously, there you have symmetry here. Okay? So this is a very important principle of symmetry. Okay, so so you don't always have symmetry. You can't always use symmetry in physics problems, but when you can, you should use it because it saves you a lot of work. Okay, so now we've using conservation of momentum and a combination of, you can either think of it as conservation of energy or symmetry. At this point over here, we know the velocity, and then we say, okay, well, what's then the final velocity over here? Okay, so the final velocity, you can just sketch it. Okay, all velocity vectors are tangential to the trajectory, so you know it's got to be in that direction. You also know that because the diver is falling through some height, there will be some gravitational potential energy converted into kinetic energy, and so they're going to pick up speed. And so this vector is longer than this vector. It's tangential to the trajectory. So that'll be the final velocity vector. Okay, and the x component of it, well, we know that. It's the same because there's been no horizontal forces acting. The Vx final here is equal to Vx initial. Okay, so we have that. And so all we need to figure out is this Vy final. Okay, and so we can figure that out again by using, say, conservation of energy. So conservation of energy. Okay, so how do we do that? Well, we say, okay, there's some, the kinetic energy final at that point over there is going to equal the kinetic energy it had here plus the gravitational potential energy, or the energy that came from the gravitational field. So that's going to be plus, it's going to be larger, it's going to be plus mg times the vertical height they fell through, which is h, plus mgh. And now that you know the final kinetic energy, you know that the kinetic energy is 1/2 m times the speed squared. And so immediately that tells you what v final, the speed, is. So now you know the x component and the speed. So then by just a little bit of trig and stuff, or a little bit of algebra, Pythagoras's, you can then figure out what v y final is. And what else? And the angle, theta final. Okay, and then so you get some numbers, and then you check those numbers, and you say, well, so this is a really important sort of point here. You just sort of check at the end of the day. You say, well, obviously I need this final speed to be larger than this initial speed, or this speed over here. So, you know, check. Is your numerical answer for V final, you know, bigger than your numerical answer for V initial? If it's not, you made a mistake. If your V final is 3 times the speed of light, it's wrong, right? Are there these reasonable numbers? Like, did the diver hit the water with the speed of like a few meters per second, you know, 5 meters per second or whatever? Okay, and then also, you know, these angles. You know, think about these angles. So there's an x component here that's the same. The y component here is longer than the y component here. So it must be that this angle, theta final, is greater than theta initial. So check, is theta final greater than theta initial? So all along the way, you should be like, you know, sort of double checking things. At the end of the day, you shouldn't be, you should be absolutely certain that you have the right answer because you've checked things along the way. You've done double checks here and there along the way, and it's all consistent, and you get numbers that make sense. And so you can be pretty sure that you're right. Okay, so this is just sort of an illustration of how it is you might solve a physics problem. This is what the solution to a typical physics problem looks like. What you're doing is you're trying to articulate your thinking. Okay, clearly, what are the principles involved? What was my thinking here? You know, all that kind of stuff. Draw pictures to illustrate so that you can explain your ideas clearly to somebody else. A super important skill. And during the group sessions, you're certainly going to be doing this kind of thing. Okay, so I don't expect you to all to be, so fluent and, with solving problems like this, like right away. But certainly, this is the sort of thing you're trying to work towards. Okay, I don't want to see solutions like this. X final is equal to X initial plus this, and then you plug in, 6 plus 4, and then you're done. Right? This might be the answer, as I said, but it's not a solution to a physics problem. A solution to a physics problem illustrates your full understanding of the problem and all of the thought processes that led to the solution. Okay? It's a great sort of exercise, a great way to start thinking, work in that direction. All right, very good.